Hello, this video is going to be a walkthrough of how I was able to derive or prove out the formulas that are used to calculate the miter and tilt angle when constructing polygonal bowls with splayed miters, as they're sometimes called. Now, if you came here just for the formulas, I'd actually recommend you just jump over to Matthias Wendel's, I hope I pronounced his name correctly, Matthias Wendel's webpage and use his spreadsheet, because that will get you up and running faster if you just want to know the correct angles to use to make your cuts, whether it's wood, metal, etc. I have the link down in the description for his website, and from there you can also check out his video. What I'm going to do in this video, though, is walk through the logic in math that I used to derive the information in that spreadsheet from scratch, using just basic trigonometry. I wanted to do it as a fun challenge, but also to assure myself that I could solve other complex geometry problems I might come across in metalworking. So this video is to help anyone else who just wants to scratch that itch and wants to understand how to derive the miter and tilt angle formulas from scratch, or to just understand how they might have been derived. I should say there's probably many ways. One of the things about trigonometry and geometry, there's many ways to come to a solution. I don't know for sure how Matthias Wendel put together his spreadsheet. I'm just showing you one possible approach that might have been used, and it worked out for me. It just happens to be the one that I stumbled upon. Now, just for a little bit of background, I recently started hobby welding and covered my first simple fire pit project in a previous video. For my next project, I've decided to build a fire pit in the shape of an octagon with these tapered staves, as they called. Basically, a geometric bowl or a polygonal bowl. So I jumped into FreeCAD software to mock up the octagon bowl and base that I want to use to support it, and I quickly realized that figuring out the angles and measurements for even a simple polygonal bowl is not very easy. I did some Googling, and I was surprised how hard it is to find the formulas and tutorials explaining the formulas. I would have thought it was a common math problem and there would be some guide and explanation either from woodworkers or mathematicians, and maybe my Google Kung Fu is weak, I'm not sure, but I eventually came across a couple of websites that I would refer you to. The first one, as I mentioned, T.S. Wendel's site. The great thing about that page is that he provides an Excel spreadsheet you can download that has live formulas in it, and with that you can look up angles in the chart and you don't have to do any math at all. As a second resource, I didn't rely on too heavily, but I think it was a pretty good video, if I pronounce the guy's name right, Kurt Einert, his YouTube video, and I'll put a link down below. It covers tapered stave math. Now, I don't mean to criticize either video, I just know that I felt that neither explain how the formulas that they use were derived to my complete satisfaction. In the case of Wendel's page, he just explicitly states on the page that he's not interested in teaching math, so fair enough. With Honor's video, he, I think, sort of explained the miter angles and the formula derivation, the approach he took for that. I don't think there was enough explanation, at least, again, for my satisfaction and curiosity, explaining the tilt angle, which I found very difficult to visualize and solve, and I'll talk more about that later. I'm not looking for any formal mathematical proofs, and I'm not going to provide any formal mathematical proofs here. I'm just sort of walking through the logic and the formulas that I used using basic trigonometry to come up with a spreadsheet that I use, that I can just put in the number of sides, the cone angle, and it will, and I'll define what I mean by the cone angle later, that I use to come up with the spreadsheet, and it matches spot on to several decimal places, matching up with Wendel's chart. So I'm happy with my result. So again, in this video, I'm just explaining to you how I figured this all out from scratch, but realistically also with a little bit of reverse engineering from some concepts introduced by Wandel spreadsheet, and I'll talk about that as well. Now, the one thing I won't be covering is basic trigonometry. It's assuming that if you're watching this, you've got a good handle on it. By basic, I mean all you need to know is good old SOHCAHTOA, which was burned into my brain from some high school trigonometry class. You need to understand what that acronym is and how to use it. Also the inverse trig functions, inverse sine, inverse cosine, inverse tangent, and what they are. The Pythagorean theorem I used a few times. And then just because the spreadsheet formulas, Excel, the formulas do not accept degrees as inputs, so you can't take the cosine of 45 degrees, for example. You have to convert 45 degrees to radians, and of course there's a spreadsheet function to do exactly that, but it helps if you just have some basic awareness of radians and the fact that degrees and radians can be converted to each other and back and forth. Again, you probably covered this stuff in high school or college. If not, or if you just need a refresher like I did, I'll put some links in the description to the Khan Academy YouTube classes cover these topics. But otherwise, I'm going to assume that you know them. So first off, let's talk about what we mean by polygons and sort of the limitations of the work I'm doing here. What I'm doing is applying to what are called regular polygons, and you can see on the screen there the precise definition. The informal explanation is it's polygons that form a circle or could be used to make a bowl. So, for example, a square. So we're talking about symmetric kind of circle-shaped polygons. The next step, and I guess this is sort of easy and intuitive, but we're going to start from the beginning, is to recognize that for any given polygon, I'm not sure I'm using the correct terminology here, but I'm talking about the internal angle, where if you make lines within the polygon connecting dots or corners that are across from each other, these angles here are always 360 divided by the number of sides. So here we're going to use a square, so a four-sided polygon, and I'm going to use a square, a four-sided polygon for all my examples here. The math will apply, and the spreadsheet proves that will work for, I think, any size polygon, but for me, just the ability to think about it and reason through things, I think a square is a good way to go. So in this case, 360 divided by 4, we know that this angle here is 90 degrees, and obviously half of that will be 45, and we're going to find that we're going to work with half of 360 divided by the number of sides quite often as we work through this, getting our final answers. So as I'm building my spreadsheet, I have here, in a convention I use, the yellow highlighted cell is a cell that is a variable, something I can change. Everything else is a formula. So we can see I already have a spreadsheet going where I can put in the number of sides. I get what I'm calling side degrees that we talked about, half of that as a useful tool. And so we have the degrees, and then also, as I mentioned, it'll be a lot easier if things are already converted into radians, and there's spreadsheet formulas that will do that here. Okay, now the next concept that we want to be aware of, and we're going to use this concept, I think, a total of 3 times to help move along our solution. And this is the idea that if we define R to be the length of the center of our polygon out to one of the flat sides, as you can see R here, and if we define L to be the length of one of the sides, that the ratio of L to R will be the same for every polygon of that type. Now, I'll demonstrate, for example, we'll figure out that for a square, the LR ratio is 2, and it is 2 for all squares. It's not 2 for all polygons, so for example, if you do a hexagon, they'll have a different LR ratio, but all hexagons will have that ratio. So once we figure out the ratio for the particular class of polygon that we're working with, that turns out to be extremely useful. Now, when I say that the LR ratio is the same for all polygons of that type. I don't have any kind of geometric proof for that. I just noticed that in his spreadsheet, Wandel had a cell dedicated to that, and that got me curious, and it seemed to work out. So I'm just assuming that it's a sort of mathematical or geometric truth that we can rely on, and I use it, like I say, 3 different times to work it out. So it's something to be aware of, and it helps the analysis. Okay, so we want to figure out L and R so that we can figure out the LR ratio for our square, and it will apply to all squares, and we'll see why that's helpful later. So in order to do that, the way I thought about it was, well, first off, from the center of the polygon out to one of the points. So from the center out to one of the points, we have a line, and a right triangle is formed by half of the length. If we consider this to be L, then obviously this is 1/2 L. So we have, again, from the center to that point where there's like a corner, and then half of L, and then R. So we have that triangle formed. So I just arbitrarily say, well, let's just arbitrarily say that we're building a bowl, and we intend for the distance from the center to the point to be 1. And I'll do that a lot throughout this analysis, where I'll just arbitrarily set the length of something to 1, and that's fine. So now I have a triangle where I know the length of the hypotenuse, I know the length of one of these angles, I know it's 45 degrees, because remember 360 divided by 4 gives us 90 for this angle here, so this has to be 45 degrees. And now I can use SOHCAHTOA, and I can figure out the length of R, and I can see that R is the hypotenuse, 1 times the cosine of 45, and that works out to about 0.70. Great. Now, using the Pythagorean theorem, a squared plus, what is it? No, a squared plus b squared equals c squared, I can figure out that 1/2 L is the square root of the hypotenuse squared minus r squared. So the square root of that works out to 0.707. Just total coincidence that these two are the same. It's not a coincidence, but it's not meaningful in any way necessarily. So if 1/2 L is 0.707, L must be 1.41. So great. Now I know R, and now I know L, and now I know the LR ratio for squares is 2. And that's going to be very helpful. So far in my spreadsheet, we have the same first 3 lines are the same as before. This from the center to a point or a corner, putting arbitrary value of 1 in there. And now, using the formulas that I talked about, we can figure out R, we can figure out 1/2 L, and we can figure out L and the LR ratio. And the spreadsheet will do all this automatically if I just put in the number of sides of my polygon. Okay. Now, let's imagine that we're looking down at the bowl from the top. So we've made our polygonal bowl. So here's the flat bottom. These are the sides flaring up and out. This side flares up and out. So we're a bird flying over the bowl, and we're looking down on it. Now, if we think about it, there's an inner square and there's an outer square. And we already know the L, remember the LR ratio we talked about, we know the inner L of the inner square. We just figured that out. So it will be very helpful if we figure out the outer L, and well, it'd also be helpful to know 1/2 of the outer L minus L. So if we think about it, outer L minus inner L, if we think about this length minus that length, that means the sort of excess must be spread out between this line here and this segment, that segment up there and this segment here, and that's going to be useful because you can already see how that's going to form a right triangle, and it'll be useful later. So for now, just inner L, outer L, and let's figure out outer L, and that will help us also figure out 1/2 of the difference between outer L and inner L. Okay, so how do we figure out outer L? Well, let's now imagine that we're looking at the side view of the bowl. So we're down on the ground. Imagine that our bowl is on the ground. We're down on the ground, and we're at eye level with the bowl. We're like a, I don't know, an ant or something, or whatever. We're looking at the bowl, and I need to introduce a new concept here, which is what I'm calling the cone angle. And the this is something that we decide ahead of time. So for example, if I'm building the bowl, how much do I want it to flare out? I don't know exactly the term for this, whether it's the flare out, the cone angle, but just think of it as the angle that's formed when you look at the side of the bowl, how steep you want that to be, and you decide that ahead of time. I just arbitrarily, for our analysis here, I'm going to say it's 45 degrees. Okay, you can make it whatever you want, and it's going to be a spreadsheet input, but that's what we mean by that. So if we're looking at the side of the bowl, we can see it's 45 degrees on both sides. The next concept we're going to introduce is the height of the bowl. So that's something, again, you're going to decide ahead of time, how deep is the bowl that you're making. Is it, a foot deep? Is it 1 inch deep? Whatever. So it's the height that you decide ahead of time, and I'm just going to arbitrarily, again, to make the math simple, set that to 1. So I'm just arbitrarily setting that angle to 45, arbitrarily setting the height to 1. And we can see that we have a right triangle here, and we know the length of one side. We've set it to 1. We know that angle there, and now we can start using trigonometry to figure some things out. Now, what are those things we can figure out? Well, one of those things is what I'm going to call the shadow R. So remember that this is our square inside our flat part, and one of the first steps did was we figure out R, which was the distance from the center out to one of the edges. So we know that is R. Shadow R, that's just the name I'm giving for this segment here, because it's sort of under the shadow of the bowl. We can figure out that length. And remember, we want to figure out the outer L on the outer part of the bowl. Let me go back one slide just to refresh memories here. We want to figure out this outer L. So one of the things we can now figure out is the outer R. If we can figure out the outer R, again, from the center all the way out to the wall, we can use the LR ratio to figure out what is outer L. And remember, we already know the R here. We already know that inner R. Okay, so back to the slide. Once we can figure out this shadow R, we can add the shadow R to the R we already figured out, and we'll get the outer wall R. Once we have the outer wall R, we can get the outer wall L. Okay, so the shadow R is figured out by taking the height times the tangent of 45 degrees. And that just happens to work out to 1. Now we take the outer wall R, and we know that that will be equal to our shadow R, which we know is 1, plus R, 0.7. If you go back a few slides, you'll see that we figured out that this R here was 0.7, so 1.7. So now we know the outer wall R, okay? And like I said, the outer wall L will be this 1.7 times the LR ratio, which is 2. 1.7 times 2 equals 3.4. So now we know the outer wall, this outer wall R, and the outer wall L. And you remember one of the things we were interested in is what is the difference between the outer wall L and the inner wall L, and it happens to be 2. And that will be useful later. Now, while we're here, we can also figure out what I'm calling the petal length, basically the hypotenuse of this triangle. I call it the petal length because if you think of these geometric bowls as sort of like flowers with petals that open up, I don't know, what is the length of one of the petals? That's what I'm calling it. Again, we just use the Pythagorean theorem, and we see that the petal length is the height squared plus the shadow R squared. So height squared, which is 1, plus the shadow R squared, also 1, square root of that, well, those together are 2. The square root of that is 1.41. So now we know the petal length is 1.41. So our spreadsheet so far, I've moved some things around. And again, yellow means these are variables and you can edit. Everything else is just calculated. I think we left off here where at row 10 where we had figured out the LR ratio. Now that will figure out that outer shadow R, the center to the outer wall, and from that the outer wall length, the outer minus inner wall length, half of that different distance, which will be useful later, and the petal length, which will be useful later. And you see at this point, I've also added as a variable that we can input the cone angle. Again, maybe that's called flare angle, or it's called different things. You can see how I define it, which is just the angle at which the bowl that you're making sort of flares out. So, believe it or not, we are now ready to compute the miter angle. If we think about what we have the outer L and the inner L and the petal length. So let's imagine that we're looking at the petal, or maybe it's called the stave, but we're looking at it from above. I guess another view you might think that we're looking at it is if we're sitting inside the bowl. So imagine that we're sitting inside the bowl and looking directly down on top of one of the staves or petals, or if you can imagine that your wood has been cut already to the correct size and you're looking at that petal or that stave and you're just looking at it flat on a table, that's the angle or the viewpoint that we're looking at right now. So again, we know the petal length, we know 1/2 of OL, the outer length, or the outer L, minus the inner L. We know those values. So we have a triangle where we have the values, a right triangle where we have the values for two sides, and we just need to know this angle here, which will be our miter angle. And for that, we use the inverse tangent formula of 1/2 OL minus IL divided by the petal length, and that works out to the inverse tangent of 1 divided by 1.4, which ultimately resolves to 35.26 degrees. And with that, we have our miter angle. Next, we'll move on and figure out the tilt angle. Now, before we figure out the tilt angle, this is sort of what I have in my spreadsheet so far. It's the same as the spreadsheet we looked at before, but you can see I've added the miter resolution down here in a green background cell, indicating that it's one of our answers. Okay, so let's get to talking about the tilt angle. This, for me, was very hard to visualize. I had to build a 3D model in FreeCAD. I had to 3D print a few things so I could rotate things around and look at it. It really stumped me for a long time. It was very counterintuitive or non-intuitive to me to figure out why we even need a tilt angle with material of any significant thickness. It was not intuitive at all. However, the videos from Wandel and Honored, they explain why you need it sort of visually, and they both do a good job of helping to visualize what's going on. So again, I'd recommend you check out those videos before you jump into trying to understand the tilt angle, because it'll also help understand what I'm trying to explain, which I find it very difficult to explain and very difficult with my limited drawing skills to kind of illustrate what's going on here, especially the final steps. So let's get going. Let's think about, again, we're looking at the bowl here from the side, but let's just look at a individual stave or an individual petal, and we're looking at it from the side. Now, prior, we were kind of looking at everything as if it was just a plane and didn't have any thickness, but it's going to help our analysis and be more realistic if we imagine that it actually has some thickness. So if we imagine that this is our stave, looking at it from the side view, so imagine that the bowl goes off over here where my mouse is and goes back up. We're looking at the bowl from the side and just one of the staves, and we see it has a thickness, and again, we're just going to arbitrarily set that thickness to 1. Now, what that implies, remember before when we were looking down on the bowl, we said we were a bird flying over the bowl, and we're looking down on the bowl, and we're looking inside. When it was just simple planes, it looked like this: inner square, outer square. But once we add some thickness to this stave here, we recognize that it instead looks like this, where here's the bottom of the bowl, here's our staves, and then it has some thickness that extends out and down from this edge here. So remember, we called this the inner L, our outer L. Well, now we have another L here. And yes, we're going to have to figure out what that L is. Okay? So hopefully you can visualize what I'm talking about and understand why we're making the change from having an inner L and an outer L, why we now have this second outer L. It's because we're imagining that these staves, the material has some thickness to it. Okay? One more time, our side view with thickness. So let's start doing some analysis. If we want to figure out what that second outer L is, or that third outer L, we need to figure out the distance from here. Remember, this was the edge where the outer, our second L was. So we have our inner L, our outer L. This was that edge of that outer L. This third square, first square, second square, third square. The third square is at this point here. So we need to figure out the distance from this point to this. If we imagine a point out here, and we see that we have this right angle here. Okay? We want to solve this right angle. So we know the length of the hypotenuse is the thickness, which we already defined as 1. Now, this inside angle here, now ignore this 38. That's just an artifact from FreeCAD. It means absolutely nothing. Just ignore it. This angle here is the cone angle, as I call it, or I guess maybe called the splay angle. Remember, we just arbitrarily said for our bowl that we're making, it's going to be 45 degrees. So this angle here is 45 degrees. And we can see that from inspection, where we can see how this line is going at 45 degrees. If we make a 90-degree turn, well, then to rotate this line back up to flat, it has to be rotated up 45 degrees. And we just sort of see that from inspection, just looking at it. So again, now we have a triangle where we know the length of one side, the hypotenuse. We have one of the corner angles, so we can now use trigonometry and we can figure out this length here. I call it the ridge thickness length. It's sort of the ridge on the end of the bowl. It doesn't really matter what we call it, but I'm calling it the ridge thickness length. And that math works out to this hypotenuse, the thickness, hypotenuse slash thickness, times the cosine of the angle we know, 45, and that equals 0.7. So now we know the ridge thickness length, and hopefully you see where this is going. We can add this on to, remember we have the inner R that ends here, the outer R that ends here. Well, now we can have another R and then use our LR ratio, but you see where this is going. Okay, and just as I said, we have our R that goes, we already figured out that the R that goes to this second square, we already figured out that's 1.7. We just figured out that this little segment here is 0.7, which means that the distance from the center all the way out to our third square side must be 2.4. And using the LR ratio, we can figure out the L, the length of this outer side of our third square. The length of the side must be this 2.4 times the LR ratio. 2.4 times 2 equals 48. Okay? Now, visualizing the next step is really the hardest. I spent a lot of time rotating the CAD model, thinking, printing things out so I could, and with my 3D printer, so I could have it in my hand and just kind of look at it. It's hard for me to draw and give a visualization of what's happening. I'll try my best by sort of sharing the 3D model and rotating it on the screen. Maybe a better artist could improve upon my explanation. Don't know what to tell you, but once you see it, you'll get it. But seeing it is hard. And by seeing it, I just mean visualizing where are the right triangles. So I think it helps trying to understand this next step is to model things up in CAD, and once you do that, it becomes clear. So this well, at least clearer. And this is one of our staves, and as I move it around in space to try and explain, this is what one of the staves look like. If we look at it from the right, this is what it will look like. Remember, it's kind of like what we draw, how it's a line here and a line here, and the thickness is, as I move my mouse across, that would be the thickness. That's what it looks like from the side, and the flat part of our bowl is here, and this is sort of the petal folding out, and this is the thickness of the material. Okay, and as I sort of move it along in space, you see that you get this sort of face that looks like a trapezoid, which you already know by looking at any completed polygonal bowl that it looks like a trapezoid. And you notice we also get a trapezoid along this flat side here that's going to make contact with the bottom of our bowl. This is sort of a piece that's going, the piece on both sides that's going to touch the next stave, the stave right next to it, and interface with it and perfectly seal things up with no gaps. And you notice it's sort of got this diamond-ish shape. If we move around to the back of the stave, we see we have another trapezoid shape on the back. And again, if we, some of the lines we've been looking at, this line here, that's in yellow, that's our inner L. This, or the L of the first square we looked at. The second square, that's this line running across the top here. And then the third square, outer square, is this edge along here. That was the third L that we figured out. There's also a sort of bottom side to things, which is also another trapezoid, and we see through inspection that, and it makes sense when you think about it, that the miter angle on all the trapezoids is the same. Okay, and so you pick up on things for a while, and you realize that this surface here that interfaces with others, this represents our cut, our tilt angle cut, and we see that it is possible to think of this as a parallelogram, and you can imagine that there are lines running. A line can run at a right angle to this line and this line, and form a sort of right angle there. And we're going to pay attention to this corner here, and then a line that would run at a right angle from this line along here. So touching that point, and then a right angle along that point there. Start thinking about. and we're going to work our way up. Okay, so we're going to imagine that we're looking at one of our staves or pedals from the bottom view of it. So we're underneath it looking down, or if you can imagine that we've flipped it over on, it's a one piece ready to be installed, but we're flipping it over on our table and just looking at it. Hopefully that makes sense. So remember, what we already know the thickness here. Okay, that's our thickness, is the height of the stave actually, because again we're looking at it from the bottom, like the bottom underside of it. And I think it will help orient things if you realize that this is the thickness. It helps it'll help you understand what view we're looking at, and we're looking at it from the bottom or maybe the back side. Again, I wish I could explain it better. It's, as I've said a couple times, just got to kind of rotate things around in your mind, and hopefully it'll start to make sense. But remember that this is the length of that outer side that we figured out already was 4.8, and we figured out that the second L that we figured out for that second triangle was 3.4. So we know then that the distance between this point and a line dropping down at a right angle, so here and here, is half of the distance, the difference between 4.8 and 3.4, which is 0.7. So we know that this length here is 3.7. We know, and I'm just going to say from inspection, that you'll realize once you make several of these and look at them, that this angle turns out to be our miter angle, which we already figured out in previous step. Remember, our miter angle we figured out is 35.2 degrees. So we know the angle and we know the side. So from this point here, which again is where this drops down, this point here, we're going to create a segment. Imagine one exists that is perpendicular to this line here. Okay, and we get a right angle from that. As to why we do that, it'll be clear in a minute, why we're trying to figure out this triangle here. And I'm going to call it the stave bottom segment, for just to give it a name in the spreadsheet, and so on. So we want to figure out this stave bottom segment for reasons that hopefully will be clearer later. So to do that, the cosine of 35.2, which is the cosine of our miter angle, which we figured out in previous steps, times our hypotenuse, 0.7, gives us 0.57. So now we know this length here. Okay, we're going to jump back into FreeCAD just for a minute, because I want to have you look at the stave from the side again and recognize that and talk about that blue line for a minute and what that is. And just to clarify the view, we're looking at the bowl from the side, let's say the right side, and off at a little bit of an angle. That's our viewpoint. You can kind of see the orientation in FreeCAD up here. This is sort of the face of the pedal. So the inside of the bowl is this surface here. This surface here, this whole gray plane here, this is the surface that interfaces with the stave next to it and touches the stave. And so this blue line, we want to imagine it that it runs from this point here along this face. So don't imagine any depth to this blue line, just it runs along that face to there at right angles. And let me see if I can get this in the right orientation so you can see how it's a right angle there, because it's very hard to visualize, and it's not intuitive that this can be at a right angle to the lines of your parallelogram. So that's the line you kind of want to visualize, and I'll show why that's useful in the next step. Okay, so we have our next and actually our final step where we'll finally be able to calculate the tilt angle. So we were just looking at this shape in FreeCAD, and now there is a right triangle that we're going to compute, and I've done my best to kind of draw it. So we have this blue line, and remember what that blue line is. Now remember that we already figured out one step ago, the stave bottom segment length. So if you imagine from this point here, there's a line that sort of penetrates inside the body of the stave, and that line is also at a right angle to the back line that runs along the bottom here, this black line. You can see that you imagine this goes off, and that's sort of the back of the stave. And where these two meet is the corner point here that comes up, okay, and that height would be the thickness. So we now have a triangle, a right triangle, where we know this length here, the stave bottom segment, we know the thickness, we said that was 1, and then from that point it runs down along this blue line, which must mean that this inner angle here is our tilt angle. So I have no idea how other people are viewing this, or whether my artwork here helps, but you just have to imagine this line is in 3 dimensions, goes inside of the stave through there, and is at a right angle to the line along the back bottom there. And if you do that, now you see there's a right triangle that is, and this blue line is at a right angle to these two, this line here and this line here, and I showed that before by tilting things just the right way in FreeCAD so you could see it. So again, now we know that this angle up here must be our tilt angle. So since we have a right triangle where we don't know the length of the hypotenuse, we don't necessarily need that, but we know the thickness or the height of this leg of the triangle, we know the length of this leg of the triangle, so we can figure out this tilt angle using the inverse tangent function, which the inverse tangent of the stave bottom segment divided by the thickness, that's based on our previous numbers. The inverse tangent, 0.57 divided by 1, is 30 degrees. And now we have our tilt angle, and we're done. This is what my spreadsheet more or less looks like now. As you can see, the yellow represents variables that I can put in. So I can put in the number of sides, I can put in the cone angle, which is again or the flare angle maybe it's called, of how the bowl is going to go out, the height of the bowl, the center to the point, and the center to the point, that is sort of, you think of that as shorthand for the width of the bowl, depending upon what shape you have. And then the green represents the final formulas, the miter, 35.26, and the tilt angle works out to exactly 30 in this case. And if I just change the number of sides or change cone angle or both, all these cells are formulaic, so they all will update automatically and give me the correct miter and tilt angle for what I'm doing. My final comments, there is a minor issue with my spreadsheet. It gives the divide by 0 error in the tilt computation for 90 degrees of splay, or the cone angle of 90 degrees. But obviously in that case, the tilt angle is always 0, so I don't really care about that problem in the spreadsheet, because obviously the answer is 0, and I could fix that if I wanted to. Probably my approach was to give almost every cell I created a named cell. It probably all could be combined into one long formula instead of a bunch of interrelated cells, but I'm okay leaving it as it is. I definitely thankful to Wendell and honored for producing the content that allowed me to reverse engineer this problem, especially Wendell's spreadsheet and the revelation about the LR ratio, which helped me a lot. I probably wouldn't have bothered to do it, and probably couldn't have done it without having, at a minimum, having correct solutions that Wendell provided in the spreadsheet to double check my work. Many times I thought I had solved things and my numbers were a little bit off or sometimes way off from Wendell's, and that let me know, okay, I'm wrong. I need to go back and figure out my mistakes. So definitely a debt of gratitude to him for publishing his work, which allowed me to do here what I did. Leave me a comment if you feel like you need my spreadsheet or FreeCAD model, and I'll try and get it out to you. I hope this was helpful to someone. Hopefully I'm not the only crazy person out there who isn't just satisfied using a formula but wants to understand how the formula works or why it works, or see an informal proof of the formula. Here you go. Thank you, and good luck with your projects.